Hi, I'm Samuel Carvalho, and this is the work using Grammatical Evolution for modeling energy consumption on a computer numerical control machine. So this work was done by me and my colleagues Joe Sullivan, Enrique Naredo, Douglas Mota Diaz, and Conor Ryan in both the Limerick Institute of Technology and the University of Limerick in Limerick, Ireland. So a brief overview of this work. So this paper presents a case study on the use of GE for modeling energy consumption on a CNC machine. And we introduce a new grammar seeding approach based on the autocorrelation analysis of the training data. And we believe this approach can be applied to other GE-based time series modeling problems. And also the proposed method in this paper uses only energy data and was capable of generating models that match or outperform the ones currently seen in literature. Just a quick introduction on CNC machines. So they are mostly used for the manufacturing of metal parts, so they can manufacture from airplane seats to prosthetic bones, for example. And one thing that is common to all of them is that they are highly energy demanding, basically because they have many subsystems running at the same time when these machines are working. So there's like cooling, lubrication, logical circuits, electric motors, and so on. So there's a lot of sub-circuits running in a machine like this, and therefore it's a highly energy demanding machine. As these machines work on the parts they are machining, basically the energy consumption varies consistently while they're working. And then these energy profiles are created for each part. And when we have many of these, what we call the energy fingerprints of each of these parts machined, we can see this interesting time series data, which basically consists of the consecutive parts being machined by the CNC machine. And here we can see also kind of a deeper explanation of each of these profiles that we can actually link to each step of the process, such as the machine starting, ready for operation, the spindle starting, and all of these different stages that these parts would take. They can actually be kind of mapped back to the energy consumption of the machine. As the motivation for this work, so basically measuring, analyzing, and understanding the energy profiles can generate a lot of useful knowledge to the industry practitioners. And also improvements can be achieved not only on the energy consumption of these machines, but also using this information we can work on production planning, predictive maintenance, for example, and many other decision-making processes that could benefit from this information. So basically for these reasons, several studies have already focused on the modeling and simulation of the energy consumption on CNC machines. And here we have just a few examples of papers on the subject. So 4 papers here basically exploring the simulation, the modeling, and the understanding of this energy consumption on CNC machines. Then as the motivation for this work, basically we believe that a grammar-based approach such as GE is a good candidate for generating accurate models in this specific problem. And for a few reasons we believe this. So basically GE can find optimal or close to optimal solutions in this case. Grammars can be fine-tuned to incorporate expert knowledge and problem-specific information. And also the scope and complexity of the resulting solutions can also be controlled by the grammar design as well. So there's a lot of flexibility by using grammars in this case. So starting with our experimental setup in this case on the data acquisition. So as mentioned in this work, we propose the use of GE for modeling the energy consumption of a CNC machine for specific products in this case. So we have 3 specific products. So to get data from this machine, this is basically the setup that we have used here. So we have the electrical panel, kind of feeding, supplying energy to the machine. So we had these AC sensors connected to a PLC, and this PLC sending the data to a database from which we read this information and provided these to the analytics engine, which in this case is basically our GE algorithm. 3 data sets were acquired using this setup. So each one was covering 24 hours work shift that alternated between periods of production and idleness. So it's also important to model how these machines spend energy when they're sitting idle, because even in idle they are actually consuming a lot of energy because of all the subsystems. Each data set corresponded to the machining of a specific type of product, and these data sets were split between training and test data. So basically 16 hours for training and 8 hours for test in each of these 24 hours data sets. And we have used the training root mean square error to drive the evolution, and the test RMSE was used for reporting results, basically. On the evolutionary setup for these experiments, we were using the libg API. So it's a C++ based API, and we were evolving basically auto-regressive models. The models were loaded, simulated, and assessed in GNU Octave, which is a kind of an open source alternative to MATLAB. And we were using a test bench approach in which we would load, for example, 100 different models and test all of them in a single execution inside Octave. On the parameters used in the evolution itself, we have used 100 generations with 150 as the population number. We have run 30 different runs for each experiment, so we get statistically significant output from it. We have used a crossover rate of 0.7 and a mutation rate of 0.3. Both were found empirically basically, so we've tested several different numbers for these rates before actually running the final batches. The selection method was the roulette wheel, and the fitness metric, as mentioned, was the root mean squared error. On the grammars design, we have used a seeding approach for defining grammars for each type of product. So basically, since these consecutive energy profiles from production, they get close to a periodic time series. So what we have done is to use an autocorrelation analysis on this data to extract what we call relevant timing information from this time series. So this information was then incorporated into the seeded grammars as a set of relevant constants. So just an example on the autocorrelation analysis. So here we have an autocorrelation graph from the product 1. Basically, we can see here highlighted the 5 most correlated legs. So these were made available as options to the auto-regressive models on the seeded grammars. So next we have an example. So basically we had 3 classes of grammars for each type of product. So the grammars G1, they were the original or the baseline grammar, which would include the 24 previous observations. The grammars G2, they were seeded grammars, including only the 5 highest correlated past observations, as shown in the past autocorrelogram. And also G3 was the 3rd class of grammars, which we call the trivial plus seeds grammar. So basically these grammars would include the trivial term, which is y of k minus 1, and the 5 highest correlated past observations. So as we had 3 different products, these resulted in 9 different experiments alternating between the different products, and the the three different grammars as well. And here we have examples from the grammars used in product 1. So basically on the G1, so the first grammar we have, as mentioned, the 24 previous legs, or the 24 past observations available to the grammar. Here we have only the 5 highest correlated observations, past observations. And here we have both the trivial term here up here, a constant multiplying y of k minus 1, and also the 5 highest past correlated observations. On the model assessment, so the goal here was to evaluate how accurate these resulting models would be as proxies for energy consumption. So what we have done is to take the output from the best models and compare it to a new set of empirical data sets. And these comparisons were done inside a pre-existing analysis tool that extracts information from energy profiles. So this tool is called the IS4Prod app. And both the model and the empirical data sets were compared on 5 metrics that the app can extract from these energy profiles. So basically the number of produced parts, the number of hours producing, the number of hours idling, the average kilowatt, and also the total kilowatt hours, so basically the energy consumption. And here these are just screenshots from the app itself, so we can see that the energy profiles were loaded into the app, and then we can see some of these quick insights. So for example, the number of produced parts, production and idle times, and all these different metrics. Also energy OEE, time OEE. So these are all metrics extracted from the app. On the results, so basically starting with the mean RMSE over the 30 runs for each scenario, so basically each of the products. So here we can see that there is no significant difference between grammars 1 and 2 for the 3 products. The p-values ranged from 0.46 to 0.89, but grammar 3, or the trivial plus seeds grammar, presented the worst mean RMSE for the 3 types of product. So we can see on the 3 graphs here, the grammar 3 is this black solid line in all of them, and all the grammars 1 and 2 are represented by the dotted red and blue lines, and we can see that they are not so different to each other. However, despite resulting in the highest mean RMSE values, grammar 3, or the trivial plus seeds class of grammars, was capable of finding the best individuals in all scenarios. So here we can see the best RMSE over the 30 runs for each of the scenarios, and grammar 3 was actually capable of finding the best model in every case, for every different type of product in this case. Then on the model assessment phase, so basically these are the best models for each of the experiments. So products 1, grammar 1, for example, product 2, grammar 1, and so on. So these are the auto-regressive models that we have found to be the best ones in each case. And then here are the results from the IS4Prod app. So we can see that the 5 metrics are here. So produced parts, hours producing and idle, average kilowatt and total kilowatt hour. Here we have the empirical results, so the actual results from the data set. And here the predicted results from the model. And we can actually correlate, so the best models in all scenarios were actually using the grammar 3. And if we see the difference here between the empirical and predicted outputs, we can see that the difference is very low on percentage in pretty much every case, which kind of confirms our hypothesis that GE was a good candidate for generating models for this problem. So coming to the conclusions of this work, as mentioned mentioned, GE was capable of evolving accurate models for energy consumption in this case study. All the resulting models matched or outperformed the results currently reported in literature for equivalent problems. It's hard to compare specifically the same metrics because the works are kind of different to each other, but many of them report accuracies around 90 to 95%, which is also what we have seen in this work as well. We could also see that seeding grammars with relevant constants as well as expert knowledge can improve results from evolutionary methods. So in this case, we were using this autocorrelation analysis to seed the grammar with important constants. In this work, only energy data was used, while some other similar works include specific machine parameters in their models. So we believe because of that our approach could be easily transferred to other discrete manufacturing scenarios because we are only using energy data. And on future work, we believe that the future work could extend the types of models and problems addressed by this method, as well as further investigate the use of relevant problem-specific information in the grammar design. As mentioned, in this case, we have used autocorrelation analysis, but pretty much any, let's say, previous analysis of the data can be used to seed grammars and reduce the search space and try to find best output from it. So yeah, that's it from me. Here are my contacts in case you want to connect with me. And this QR code will bring you to the full paper. Thank you.